Welcome to the cast on Descriptive Statistics, its concepts and applications. The content is developed by Jitendra Tomar, a corporate consultant, and is designed at JT Design Studio. Let us discuss the concepts in detail.
We're swimming in data every single day, right? From sports stats to sales reports, it's just everywhere. But how in the world do you take all those numbers and find the actual story hidden inside? Well, that's exactly what descriptive statistics is for. And today, we're going to learn how to use it to turn all that chaos into crystal clear clarity.
I mean, look at this. When you're staring at thousands of data points, it's pretty much impossible to see what's really happening. It's just noise. Descriptive statistics are basically our toolkit. Think of them as a set of magnifying glasses and highlighters that let us zoom in, find the patterns, and pull out the one simple story that actually matters.
So, where do we even begin with a messy cloud of data like that? Well, the very first thing we've got to do is find the center of it all. We're on the hunt for that one single typical number that can stand in for the entire group. In the world of stats, we call this finding the central tendency.
And our go-to tool for this, the one you probably know best, is the mean. Yep, it's just the good old average. It's pretty much the workhorse of statistics, giving us a super quick snapshot of the data center point.
And the way you calculate it is super simple. You just take all your values. Let's say we have 3 exam scores, 80, 85, and 90. You add them all up, and then you divide by how many there are. In this case, 3. Boom, you get 85. That's our mean. See? Simple, but it's a really powerful first step.
Okay, but the mean has a bit of a kryptonite. What if one of those students completely bombs the test and gets the 0? Suddenly, that average of 85 takes a nosedive, and it doesn't really feel typical anymore, does it? For situations like that, we need the median. The median doesn't get rattled by super high or super low scores. It is simply the value that's right in the physical middle of the line after you sort all your data.
So, picture this. We line up 5 numbers, 10, 20, 30, 40, and 50. The one smack dab in the middle is 30. That's our median. Super easy. No heavy math, just finding what's in the center of the line.
All right, so we found the average with the mean and the middle with the median. But what if we're not interested in either of those? What if we want to know what's the most popular? Well, that's where the mode comes into play. The mode is just the value that shows up more often than any other.
Imagine you're looking at a list of recent sales. You see the number 7 pop up more than any other number. Well, 7 is your mode. And for a business, that is gold, right? It tells them exactly which product is flying off the shelves.
Okay, so finding the center is a great start. But honestly, it doesn't give us the full picture. Not even close. To really understand our data, we have to ask another question: how spread out is everything? And this is what statisticians call dispersion.
Let me ask you this. Let's say 2 different classes both get an average test score of 85. So did they perform the same? No way! It's possible one class had everyone scoring right around an 85, but the other class could have been all over the map, with some students acing it and others failing completely. The average, all by itself, completely hides that part of the story.
So the quickest, simplest way to get a handle on this spread is the range. And it's exactly what it sounds like. It just measures the total distance your data covers, from the absolute lowest point all the way up to the absolute highest.
The calculation is dead simple. If the highest number in your dataset is 25 and the lowest is 5, you just subtract them. The range is 20. It's a really quick and easy snapshot of the total spread.
But here's the catch with the range. It only cares about the 2 most extreme points, the absolute highest and lowest. What about everything else in between? That's where variance comes in. It's way more sophisticated because it looks at every single data point and figures out, on average, how far away it is from the mean.
Okay, I know what you're thinking. Those formulas look a little scary, but don't worry about the math right now. All they're really doing is measuring the average distance of every single point from the center. All you need to know is this. A big variance means your data points are all over the place, scattered far and wide. A small variance, that means they're all huddled up together.
Now, variance has this one kind of weird quirk. Its units are squared, like squared dollars or squared test points, which is confusing, right? To fix that, we have the standard deviation. It's just the square root of the variance, which brings us back to units we can actually understand and makes it so much easier to interpret.
So here's the bottom line, the thing you really need to remember.
A low standard deviation tells you your data is super consistent and predictable, like a super precise machine turning out parts that are all nearly identical. A high standard deviation means your data is unpredictable and all over the place.
Okay, let's recap. We've nailed down the center of our data, and we've measured how spread out it is. But there's still one more piece of the puzzle, the shape. I mean, if we were to graph all of our data points, what would it look like? Would we get a nice, perfect hill, or would it be all lopsided?
And the first tool we use to understand shape is called skewness. Basically, it answers the question, is our data perfectly balanced and symmetrical, or is it leaning to one side?
And this visual makes it super clear. A symmetrical distribution is that perfect bell shape right in the middle. A positively skewed one has a long tail dragging out to the right. A classic example is income data. Most people are in one area, but you have a few billionaires that stretch that tail way, way out to the right. And a negative skew, the tail just points to the left.
All right, our last measure of shape is a fun word, kurtosis. All it's really asking is, how pointy is our data? Do we have a sharp, steep mountain, or is it more like a flat, broad hill? So if you see a really sharp, pointy peak, like that top image, that's high kurtosis. It means a ton of your data is crammed right into the middle. And if it's flatter, more like a plateau on the bottom, that's low kurtosis. The data is a bit more evenly spread out.
Okay, mean, median, variance, skewness. I know it can sound like a lot of abstract math, but you might be wondering, why does any of this actually matter in the real world? Because these aren't just terms from a textbook. They are the exact tools that people use every single day to make huge decisions in business, science, and finance. Let's look at a few examples.
Well, think about it like this. For a stock trader, standard deviation isn't just a number, it's risk. A high standard deviation means high volatility and probably high stress. For a marketer, the mode tells them their best-selling product. That's the one they're going to put front and center. And in a factory, the goal is a tiny standard deviation. That means every single item coming off the production line is almost identical and top quality. These numbers are running the world behind the scenes.
So what we've seen is that descriptive statistics gives us this incredible power to look at a mountain of past data and make perfect sense of it. It is the absolute foundation of all data analysis, but it also leaves us on the edge of our seats with one really big question. Now that we can describe the past so well, what can we predict about the future? And that is where the real adventure begins.